Hello, Andoyo. Can you hear me?
Hi, Per. Hi, Per. How are you?
Hi,
Yes.
good.
Good morning.
Yeah, good morning. Yeah, I guess it's afternoon.
Yeah. How are you?
No, very good. Yeah, it's looking forward to this lecture. And
Yes.
yeah, it's it's still winter in Oslo, Norway, but
Yeah. How degrees?
yeah, it's close to 0, I think, but it's
Oh
sunny
my.
and blue sky outside, so it's yeah.
Yes.
But I'm actually traveling to California on Saturday to visit some former colleagues at Stanford, so I'm gonna work a little bit there for a couple of weeks. So I get a little
it's nice.
warmer.
Yeah. Here is
temperature.
as you know, here is tropical country. Yeah. It's
Yeah.
little
It's the
bit
same
hot
temperature.
and humidity. Yes.
Very good. Yeah.
Okay, we will wait our rector, and yeah, we will start when he come. It's
Yeah.
okay?
Yeah, sounds good.
Okay. Thank
Very
you.
good. Yeah.
Selamat sore Pak Hadi.
Iya, selamat sore Pak Andoyo. Kayaknya
Iya.
Biskom ya. Saya sama
Iya.
Pak Rektor bilang, aduh saya bilang kayaknya nggak ada deh kalau saya tanya Pak Martin ini.
Iya. Iya itu ya mohon maaf.
Nggak apa-apa. Maka saya bilang Mas Martin kalau lain kali kabar-kabarin ke jurusan saya bilang. Saya ditanya sama Rektor saya juga bingung saya bilang.
Yes. Ya ini apa namanya? Ini tamu kita dari Norway, Mas, salah satu honorary professor yang nanti insya Allah mau ke ITERA sih di akhir tahun ini. Sementara ini beliau mau ngasih e-lecture ke kita.
Oh, okay. Akhir tahun ini berapa lama, Mas?
Saya belum tahu fixnya beliau, nanti kita ikuti ini.
Kalau nanti dimanfaatin aja masuk selama di sini.
Betul. Kita inilah pokoknya kita arrange.
Oke.
Sementara sih Pak Rektor bersedia, tapi nanti kalau seandainya ada kabar terbaru, kita Mas Hadi siap-siap Mas ya.
Ya, siap-siap.
Tapi sementara masih on schedule sih.
Katanya sakit Pak Rektor tadi pagi, tapi
Sakit.
flu gitu.
Oh, flu ya.
Mudah-mudahan
bisa. Okay. Hi, I changed my account. Oke. Mas Adi, bisa dengar suara saya? Gimana?
Rektor juga sudah hadir ini.
Oke.
Bisa.
Oke, kita mulai ya. Baik. Good morning, Per from Oslo, and good afternoon, all audience from Indonesia. Today we have a special guest lecture from our honorary professor, Dr. Per Avseth from Norway. Today he will give us a very insightful topic about geophysics. And for the first session, we have our rector, Professor Dr. Inyoman Pugek Arianta. Thank you, Pak Rector.
Thank you,
Yeah.
Dr. Handoyo.
Okay.
Congratulations once again for your
Thank-
just achievement.
Okay, thank you, Pak Rector. Now you have an opening speech, Pak Rector, to greeting all audience and our guest lecture. Please, Pak Rector.
Right. Assalamualaikum warahmatullahi wabarakatuh. May God's peace and blessing be upon us all. We thanks God Almighty due to His mercy, His graceful. We are able to gather in this afternoon. Very joyful situation. Particularly special and honorable and grateful situations. We have Professor Per Avseth. I'm sorry, I cannot pronounce properly. How do you? I call you
Per Avseth.
Per Avseth. Okay, Professor Per Avseth. We are very grateful to have you on this webinar activities this afternoon, organized by our study program of geophysics, I think. Yeah. First of all, we would like to say thank you and appreciation, highly appreciate for your willingness to become of our big family of Institute Teknologi Sumatera, a new campus, just 8 years old now, if considering as human being, just second grade, second grade of the age of the university, and is planned to be one of the playmaker for creating human resources in the future in Indonesia. After we have two big institutes who dealing with science and technology, you probably aware, first in West Java, Institut Teknologi Bandung, and the second one in East Java, Institut Teknologi 10 November in Surabaya. So those two institutes quite old already, but it's not enough for Indonesia to create engineers, scientists to deal with future development of Indonesia. So Institute Teknologi Sumatera is designed, is expected to answer the future demand of Indonesia in terms of creating or producing skillful human resources, especially in western part of Indonesia, in this case Sumatra Islands. So once again, our appreciation, we are very grateful in your participation and your contribution to our country for future of Indonesia. We once again thank you very much. So I hope we can see face by face in not very long. You can visit our campus here in Lampung due to Dr. Handoyo later on. So without further ado, I just would like to let the seminar begin. The topic, I personally believe this is very important topic, especially for this region, as you probably very well understand, part of region which is very, very heavily or routinely facing the natural disaster due to the earth phenomena. So your contribution in this case, sharing to our student, will be very, very helpful, very useful, very, very important to give them understanding about the earth phenomena in the future of Indonesia. So once again, thank you very much. Enjoy the discussion. I also will try to catch up later on because I'm still at the moment doing other occasions. So please excuse me just to leave you for a while, and I will come back later on. Thank you, Professor Avseth, for your contribution, and welcome to Institute Teknologi Sumatera. Please,
thank you very much.
Dr. Handoyo.
Okay. Thank you, Pak Rektor. Terima kasih for the speech. Yes, we hope Pak Avseth will come to our institute in this year. Yeah, I hope. Yeah, we hope together. Okay, thank you again, Pak Rektor, for the speech. And now we have the main session about the e-lecture from our guest lecturer. First of all, I will like to introduce Dr. Pak Avseth. A moment. Yes. Yes, I will read yes, this is the short CV from Dr. Avseth. Yeah. He has education background from the PhD from the Stanford University. The thesis topics, the combining rock physics and sedimentology for seismic reservoir characterization of North Sea turbidity system. Current professional employment is in the NTNU, Trondheim.
consulting researcher and lecturer in reservoir geophysics. And from 2017 until now, he works in Dig Science AS in Oslo as a co-founder and lead of Geophysicist and CTO. This is the big honor for us, for ITERA, because Avseth is agreed to be our honorary professor in ITERA. And thank you so much again for your willingness. And this is also the key publication, some publication, the latest publication. And of course, we believe the publication is many more than in the slides. Yes, now it's the time for you, Avseth, to give the lecture for our students, and also for your information, our participants is now it's more than 100 people, 100 students. Is it's come from our institute, of course, and also public university in Indonesia. The students, across Indonesian universities. So yes, thank you for the participants for the enthusiasm to this lecture. Okay, Avseth, the time is yours, please.
Thank you so much. Thank you very much, Andoy, and thanks also to your rector for introducing me in such nice words. I'm very, very pleased and honored to act as an honorary professor for your institutes, and I'm very happy to give this lecture today. Let me just share the screen, and then I'll see. Someone just give me a second, and I will just share the right one. Let's see. Like this. Can you see this in presentation modes now, Andoyo?
Yes, it's perfect.
Maybe take a couple of seconds before it comes up.
Yes.
Very good.
Okay, go ahead.
So again, thanks a lot. I'm very pleased to act as an honor professor for your institute, as I said. Today I'll give an e-lecture. It's going to be around 1 hour. Feel free to, if there's something unclear during this talk, ask questions. Or we can have a discussion and questions at the end, of course, as well. And of course, as you said, I will be very, very happy to give a live lecture later this year at some point. I will be very happy to visit your campus. I've never been to Indonesia. I've been to Kuala Lumpur before, giving courses there. So I've been in the, let's call it a neighborhood, relatively speaking. But yeah, it would be very great to visit, and I hope to do that quite soon. The title of this talk today, of course, your background is probably diverse. Some of you maybe more majoring and focusing on geophysics, and others on geology. Actually, my talk is quite integrated. It's in a crossover area between geology and geophysics. And my expertise is rock physics. And the word rock physics is actually the rock is the geology side and the physics. So it is actually the bridge between the two. And my expertise and my area of research is actually to try to use tools in rock physics to bridge and understand subsurface geology from geophysical measurements. And of course, I've been mostly working with seismic data, and that's what I'm going to present today. We use well log data and seismic data. We could, of course, also use other sources of data like EM data or other. Another thing is, of course, I've been working many years related to the oil industry. So my case examples will be related mostly to petroleum. Even though the technology and the methodology could also be applicable to geothermal, to carbon sequestration. It could be for water characterization, hydrogeophysics, and it could also be more deep subsurface investigation. The role of rock physics is still important. So even though if you don't find my talk today specifically relevant for what you are looking at, the methodology I think you will find still relevant, I hope. So let's get started. The title, Multi-Scenario Subsurface Modeling of Rock Properties and AVO Feasibilities, Constrained by Depositional and Burial History. Of course, this title is including a lot. Again, rock physics is at the core. You see here is some geology, the positional and burial histories. It's about the rock types and how they change with depth. That's going to be important. And the geophysical data that we're looking at are usually AVO data, and I'm going to get back to that more in detail for those of you who haven't heard that. So it's quite an integrated approach. This is the outline of the talk. I'll give you a teaser that will illustrate the problem that we face, especially in areas where we have limited or few wells. Then we rely more on models. If you have a lot of wells drilled in an area, whether it's in oil or in geothermal or hydro characterization, if you have a lot of wells, you can use your information from the wells and maybe do some data-driven approach. But when you have few wells, you need to rely on models, and that's where the rock physics can be really helpful. And the key question is how to extrapolate rock physics properties between and away from wells. So it's an interpolation problem. It's also an extrapolation problem. So the methodology I propose, which we have been publishing on quite a lot in the last few years, is combined burial and rock physics modeling. Again, this is a bridge between geology and rock physics or geophysics. I'm going to demonstrate this in a 1D example, but actually at the end we're going to show examples.
I'm sorry, Per. Yes, excuse me. Your slide is not moved. I'm sorry.
Oh, do you see the outline slide?
No, this is the cover.
Okay, let me just switch. Yeah, so I'm gonna duplicate slideshow. Then usually it should show, I think. Do you see the outline now?
No.
Or still the... Let me just, because I have the double screen here, so maybe it's not, for some reason, it's not sharing. Let me try to, I'm going to just stop sharing, and I'm going to share again the window. Let's see. Just a second. Do you now see the outline?
Not yet.
Okay. I'll try another. Yes. Let's see. It's going to share this one. If I do like this now, you're going to see yourself first. Like this.
It's coming. It's coming. Yeah, it's perfect. It's come. Yeah, it's good.
Very good.
Yes.
Yeah, it's I know in Teams this usually works, but in Zoom sometimes
yes.
A little bit more tricky. I find it to share because I have actually 3 screens here, so I need to make sure that the right screen is showing. So now you see the outline. Good.
Yeah, it's good. It's
very good. I'll pull down this one. Okay, so I'm gonna show a teaser in the beginning, and then I'm gonna go through the methodology. I'm gonna continue with what I call multi-scenario rock physics and AVO feasibility modeling, and this is actually going to be done in 3D or at least 2D or 3D. And I'm going to show 2 examples, case examples, one from the Glitne field in the North Sea and another one in the Hoop area in the Barents Sea. Both are offshore Norway, but different regions of Norway. And then I'm going to give a summary at the end. Okay, so let's start with a teaser. How to extrapolate rock physics properties away from wells. I'll start with this figure. This is in rock physics, we like to make cross plots or look at cross plots between the geophysical domain, the measurements, the PV velocity, for example, in the vertical axis, versus the porosity on the horizontal axis. The two lines here are actually what we call elastic bounds. These are models and physical bounds. So physically, your sediments and rocks should be plotting, when you plot porosity versus velocity, within these bounds, not outside. But these bounds are very wide, so they're not very useful as predictors. They can tell you whether you have some data that are not physical. They're not, they're not good for prediction. We want to be able to predict, so we need to have better models to do that. You see some data on top of here. You see some suspensions here with high porosities and low velocities. And then you see some higher velocity but low porosity data from different data sets. And the scatter you see here and the trends are actually related to geological processes. When you change from suspensions to diagenesis and compaction of the rock, the velocities will increase dramatically, whereas the porosity will reduce. Part of my work is actually to try to even better understand this scatter. What is causing this scatter, and how can we predict these trends? Let's give you a teaser, an example. So let's say this is a 2D section, horizontal versus vertical. Let's say you drilled a well and you encountered a sandstone layer in red here, but then you have a sand prospect. Let's say it's a potential oil prospect or gas prospect away from the well. But if you don't know anything about the geology here, and it's maybe a kilometer away from this well and it's deeper, then these bounds for different mineralogies will be quite wide. So yes, the observation is here, but the properties at that well is given by these very wide elastic bounds. So these are not very useful for prediction. When I go from this well to this to say something, what is the expected properties? Because if I look at data, I need to have some understanding of what to expect before I can predict. Okay, let's see that I know the temperature gradient, and I know that the pressure, and I know the prospect is located at temperature higher than 70 degrees and pressure is higher than 20 megapascal. Then I can start making, so I have a set of rock physics models where cementation, which starts at higher temperatures, are causing the suspensions to glue together, the grain contact. So you stiffen the rock frame, and you see this, what we saw in the previous, that you can actually have models to actually constrain the bounds. So you actually get narrower bounds and better description, and your uncertainties are reducing. Okay. So now but we still don't have a good answer. It could still be quite a large uncertainties in terms of the expected properties. But if you know the geology, and you know that this is the same sandstone stratigraphy as this one, then you know that you should rely on a sandstone model and not a shale model, for example. You can constrain it more. So you're reducing your uncertainties. And then if you know your burial history, what's the history of the burial? Then you know something even better, so you can constrain it even better. So you go from this large uncertainties, by adding more and more geological information, you reduce the uncertainty, and you can actually say, and that's the whole goal. Can we actually say something about what is the expected properties away from wells to some certain degree with not too much uncertainty? I'm going to show another kind of teaser example of this. This is a seismic line from offshore Brazil. It's an old 2D regional line, and Rio de Janeiro and Copacabana Beach is approximately where my red pointer is. And then you have the shallow shelf, and then you have deep water. And in this case, it's an old line. So at that time, there was some wells drilled and log measurements made in the shallow shelf, but not in the deep water. So, and then I made a very simple geological sketch. So where you have the shelf edge and the deep water environment, and you expect to have some compaction going from unconsolidated sediments to consolidated rocks with that. So let's assume now that, yeah, we have well control in the shelf in unconsolid sediments, but then you want to look for something either deeper in burial or deeper in depositional in this direction, or maybe a combination of both. And then if we don't have well measurements, we can actually see if we can actually use rock physics models. And the rock physics models that I've been working with a lot are these so-called contact theory models. And these are rock physics models that link elastic modulus and velocities to porosities. And they relate them to the rock texture of the sands. And it honors cement at the grain contacts, which will stiffen the rock frame quite a lot. And it honors also variability in sorting, smaller particles filling in the pore space. These will have different trends in this crossplot. And then you can combine these. So you can actually explain a wide scatter with geological processes. So the question is, of course, how do seismic properties change within this basin? You could have depositional trends, diagenetic trends that we also can relate to the rock physics models. We can actually use these rock physics models or templates to extrapolate and help us to say, what if we go deeper? What if we go to more deep water environment or more deeply buried rocks? How will the rock physics properties change? So then we can understand the rock, but very often we want to know what's inside the rock, the pore fluid. So one thing is to understand the container. The other thing is which is often more important, is what's inside the pore space. I'm not going to go into the details of fluid substitution theory and Gassman theory, but this is just a simple version of it, just to give you the point. And this is an equation expressing the compressibility of a dry rock. So K here is incompressibility of rock without any inside the pore space, so it's empty pore space, is a function of the incompressibility of the mineral itself, the solid, plus this pore compressibility. So you see the porosity divided on the incompressibility of the pore space. So, and this is pretty much what is also going into the Gassman equation. And here's just a definition of the compressibility of the pore space, which is the change in volume of the pore when you have a change in the stress on the pore volume. That's the definition of the pore space compressibility. And then if you saturate the rock, you put fluid inside it, this equation that you saw for the dry rock will change to this one, approximately. The Gassman equations are slightly different, but this is the essential of it. And it's a good equation to understand the intuitive relationship. What you see here is that it's very important to know the container, this incompressibility of your container, the rock, before you can say something about the sensitivity of the fluid. It turns out that if this container is soft, the effect of the fluid will be much bigger. But if this term incompressibility is higher, the effect of what's inside is much smaller. This can be more intuitively explained. If you have a Coke bottle and you try to hold it when you squeeze it with your hands, to try to tell what's inside it, that's very difficult. If the lights are off, you're doing it in a dark room, you will not be able to tell if the Coke bottle is filled with Coke or if it's empty. If you did the same with a balloon, you could easily tell. That's exactly what this equation is saying. If you have a Coke bottle, this one will be high, and the effect of the compressibility of the fluid will have a small effect compared to the balloon. And this is essential. In the data, we measure this one, the saturated one. We assume that we know the mineral, which is normally quartz, or a mixture with quartz and feldspar for sands. And the fluid is what we want to know. But often the container is often neglected in many cases. And part of my research is really to have a good understanding of this one. And that's where the geology comes in. There's a lot of geological understanding and constraints that can help us understand this one. So we can better find out this one. And the porosity is also a function that is often empirically driven by compaction. So compaction is also affecting the porosity and the incompressibility of the rock. Okay, let's back to the motivation here. So if you have this complex geological scenario, because this becomes very important in areas with complex tectonics and geology. So let's say you have drilled a well and you discovered a sandstone interval with some oil in green here on top of water. But then in your seismic data, maybe you see something next or away from this well, which is maybe at the same depth, but it's a different age. It's Cretaceous, because it has a different geological history. The question is then, how do the rock physics properties expect to be in this location? The thing is, we need to honor the burial history, because it's not just to look at the depth itself. We have to look at the burial history through time. I'll show it with this example. So to the left, you see a burial history curve. So vertical axis here is the burial depth, which is also linked to temperature. And then the geological age is on the horizontal axis. So let's assume now you have a Cretaceous sandstone at two locations. The red is the location actually where we have a well, so we know the answer. So we can calibrate this, but it was been buried and at some point uplifted. Actually see in the geology here that has been some uplift. You see this unconformity here. So the rocks have been buried and then lifted up, and it's actually been lifted up more in the eastern part than in the western part. This means that the western part here has been spending more time at higher temperatures. These higher temperatures are actually where you have core cementation happening. So the rocks will be stiffer. Your container will be harder and stiffer. Then if you go eastward, you see some bright amplitudes in the seismic at the same level. These are interesting because if this, let's say this was a dry well and you discovered water only here, this could potentially be a hydrocarbon filling. But look, the burial history of this one is this green one. It's spending less time and maybe not barely into this temperatures. It turns out 70 degrees is a critical temperature, around 70, for onset of core cementation. I sometimes refer to this as the frying pan, where you go from sediment, mechanical compaction of sediment, to sandstone and rocks, lithification of the sediment and chemical compaction. So these over here, the green, could potentially not almost be unconsolidated. So maybe what we are seeing here is not a fluid effect, but just a change in diagenesis, that you have a soft sand and a stiff sand. Well, it's hard to know. That's why we need to do more detailed modeling. The bottom line is this behaves more like a Coke bottle because it's been cemented. The grains are glued together. So it's much harder and difficult to predict what's inside the bottle. This behaves more like a balloon. It's more easy to say what's inside when it's a soft sediment than when it's a cemented sandstone. Okay, and this brings me to the methodology that we build up for this talk. Okay, where we're going to combine this burial and rock physics modeling. This was published first time in a leading edge paper in 2016 by me and a colleague of mine in dig science, Ivan Lehoski. And it contains 4 key steps. The first is to model the burial history, as I showed you. So you have the position of the sediment, then you bury it through mechanical compaction, you go through chemical compaction, and in complex space and with tectonics, you could potentially have a big uplift. Okay. And this is the onset of cement at 70 degrees. So this is change from mechanical compaction to chemical compaction. As I said, I refer to this brownish area as the frying pan. So if the second step is then to do diagenetic modeling, we use a model called Valderhaug. There are different approaches to this, but we choose the one by Valderhaug. He is a geologist currently working with Equinor in Stavanger in Norway. And he's one of the world leading on quartz cementation modeling. So we use his models. It's a kinetic modeling that when you have this burial history here, we actually integrate over time and temperature, and that's by itself some numerical equations to solve. But then we solve that, and we can actually predict the cement volume as a function of this burial history. And you see here that it's 0 during the mechanical compaction, but when you're increasing beyond 70 degrees, you start to pick up the cement, both during subsidence, but also importantly, during the uplift phase, as long as the temperatures are high enough. And then when you're getting to colder temperatures, you shut it off again. And this cement will affect your porosity depth trends, as you see here. So here's the porosity from deposition through compaction and then uplift. And you see the porosity, even though it could be shallow because of uplift, because it's been buried deeply down and compacted and cemented, the porosity could be quite low. Then the third step is to plug these parameters into our rock physics models. And when we use this contact theory that was developed by Jack Dworkin and Ines Noor at Stanford University, where I did my PhD, and these, of course, are models I used a lot. Actually, input parameters, two of the key input parameters to these models are porosity and cement volume, in addition to pressure for the mechanical compaction domain. So you see here, these are the models for brine sands and oil sands. And you see how they are then, we're predicting the depth trends of these as a function of this burial history, both for acoustic impedance and VP-base ratio. These are two key seismic parameters that are controlling the seismic signatures. Acoustic impedance controls what we often refer to as a near stack response or zero offset response in seismic, whereas the VP-base ratio is controlling the change in amplitude with increasing offset, also called the ABO effect, or the gradient, the change in amplitude with offset. So these are two key parameters. What's interesting here is you see that the difference between oil and brine is reducing with compaction. And when you start cementing the rock, you see that the difference is becoming even less, both for both these two parameters. So the present day depth, which is the endpoint here, shows that you almost have the same properties. It's not a very big difference. And that's exactly what I talked about with the Coke bottle. When it's getting hard and cemented, it becomes much harder and difficult to separate the fluid effect than if it was just in the mechanical compaction domain without being cemented. The difference will be much larger, and you would much easier see the difference. Okay. We also look at shales. I don't show it here, but we also do depth trend modeling for shales. We usually do then more empirical models, but we can also use more physical-based models for that. Empirical model meaning that we use well-log data and create regression lines for shales. We need to know the shales because in ABO modeling, we need to know the properties of both the caprock and the reservoir, because the ABO is a function of the contrast at the layer interface between the caprock and the reservoir. And again, the burial history and the rock physics models here will project it, so we can actually say something about the expected ABO signatures. And these are the thing we're also going to extract from the data. Okay. So this is a table that was published a couple of years ago in an extended version of the 2016 paper, where we show the link between geology and geophysics. So here for different burial domains, at the surface during deposition, mechanical compaction, then chemical compaction, and then deeply buried and uplifted. And then you see the different geological processes that are occurring. And in bold, I just highlight the most important ones that we're modeling. But of course, there are many parameters, and that makes the problem, of course, complex and non-unique, and there are ambiguities. Here are the geological parameters that goes into the rock physics models, and here are the physical parameters. And then is the rock physics strategy, the models that we use to model the different cases. Okay. So then we can test and look at different parameters and see how they affect the properties, seismic properties, as a function of the burial domain. So let me give you an example. This is a synthetic example where we actually do exactly this, and it's just continuous subsidence. So in the upper left here, you have a burial curve starting from the seafloor, a thin water column. Then you bury it through time. It's Jurassic age, and this is a burial history. I just show the blue points here so it's easier to see the evolution through time and burial. And here you see the cement volume, and of course you need to have below this dashed line 70 degrees before you start picking up the cement. and it's going up to 10% here at 3,000 meters depth. And here's the porosity depth trend for sand and for shale. And here are the acoustic impedances. So this is a rock physics modeling of water sand, oil in green, and red in gas. And as you see, there is quite big difference between the different fluid scenarios. And gray is for the shale. And you see also here, it's interestingly, there's ambiguities, overlaps between the shale trends and the sandstone trends, and crossovers with that. Another interesting thing, you see that, of course, the impedances are increasing with compaction, because the porosity are decreasing. Impedance is a multiplication of velocity and density. So it will be highly correlating with a decrease in porosity. But you also see the fluid sensitivities are decreasing, as I mentioned. So you almost have no separation when you get very deep. And the sands have higher impedances than the shales when you're very deep, but shallow you could have similar or even lower impedances. The VPVS ratios are more uniquely discriminating shales and sands, and also the fluid separation with water sands and oil and gas is somewhat better with the VPVS. Again, this is one of the reasons why AVO is quite useful for lithology and fluid discrimination. In the lower left, it's just cross-plotting VPVS ratio and acoustic impedance, so cross-plotting these two. And we often refer to this as a rock physics template domain. So you see compaction trend is in this direction, and fluid trend in this direction. And the AVO crossplots of intercept and gradients is shown here, and it shows pretty much the same. Compaction trend in this direction, and fluid trend in this direction. Here's another synthetic example. So in this case, I have a burial history curve showing for a sandstone of tertiary age, 60 million years old, and is buried and slightly uplifted, but it never reached the frying pan. So it's still an unconsolidated sediment. Here's the porosity trend, and the cement display shows nothing because it was not into the frying pan. So you have no cement. It's unconsolidated. And here's the sand models. These models are actually captured by the Hertz-Mindlin contact theory. I'm not going into details of that, but it's also part of the contact theory. And these are controlled by the porosity change and the pressure is affecting it. So the increasing velocity is related both to porosity reduction and the pressure increase. And the VPVS ratios shown here, and the crossplots in the template domain, compaction trend and the fluid trend, good separation between brine and oil. And here I do from this lower left to the lower right, I actually add more points. I do Monte Carlo simulation, meaning that I put in some variability in the input parameters here. So I capture some uncertainty just to see if there's overlap. But you see here that even though I create some scatter in this data, there is still good separation because of the loose nature of these. You have very good fluid sensitivity coming out from this Gassman equation. So I should very easily be able have a possibility to separate between the oil and the brine. Brine meaning saline water. Okay, let's now try to see what happens if I dip this burial history, make it a little bit deeper into the frying pan. So I switch from this to this. I actually created slightly older rock, so it's you see now it's going into the frying pan. So I actually get the cement, a few percent only. It doesn't take a lot to glue the grains together to create a stiff rock. So the velocities increases, VPVS ratios decreases more drastically. And now you see in the lower left, look what happened here. Your compaction trend, of course, went to the lower right, and the fluid effect is much smaller. Look here. So this is the effect of the diagenesis and the cementation. You reduce the difference. And look at the AVO crossplot. You also move in this direction, and now you start to get more overlap. So it's much harder, more difficult to discriminate the water saturated or brine saturated from the oil. Okay? You just see here if it does, yeah. Okay, so let's move to a real case. Now I only showed you synthetic case. So I'm going to do this now not only in 1D, but actually in 3D. So we in DIG developed a technology to do exactly what I showed you now, but in three-dimensional space. First in 2D actually, and then in 3D. We need a lot of input data. We need the velocities, seismic velocities. If you have seismic data, you usually have velocities, either stacking velocities or FWI velocities. Also well-log data with sonic data, VPVS, density, and other what we call CPI. It's petrophysical logs like clay content and porosity logs, saturation, information that can help us calibrate some of these rock physics models. Information about sedimentology is important to know what type of facies do you expect. Is it a deep marine turbidite environment with sandstone facies mixed with shales? Or is it beach sands, shallow marine sands? That's important. And then, of course, information about the temperature history and the Burrell curves. And that's usually available from basin modelers and geologists. So we work a lot with interacting with geologists, of course, and we also in DIG, we have geologists in the team to this. So it's quite an integrated approach. We do an effort first to use the velocities. We actually create what we call net erosion and uplift maps from the seismic velocities, and then we use by combining rock physics models with the seismic velocities, and we relate that to the Burrell history. Sometimes the maximum Burrell is unknown, so it can actually help us to better constrain the Burrell history away from wells, because that also has some uncertainty to it. So create these volumes or maps of net erosion or uplift and maximum Burrell. If we have those, we can actually use rock physics model constrained by these to model the what we call AV feasibility maps or volumes. So we do exactly the exercise as I showed you in 1D. We now do in 2D and 3D away from wells. I'll show you in a second. Here is just the same in text. It's just showing the workflow. So it's the input constraints. You create the uplift map. You do this combined rock physics and compaction modeling. And then you can do this multi-scenario modeling. So you can test different parameters, input parameters. And it could be automated. So you can do a lot of scenarios and see the sensitivity. This last step, I'm going to show just briefly, but that's kind of what we are working on now, is integrating this with the quantitative interpretation. And this could also be made automated into a machine learning classification using training data based on the feasibility modeling. I'm not going to touch too much on that today. Maybe that will be a talk some other time, okay? So it's pretty much up to 4 I'm going to show today. And here is just showing the different stages of the technology. We published in 2016 how we linked the Burrell modeling to rock physics modeling to constrain the rock AVO simulations. We did it in 2D. I'm going to show some results from this, and then in 3D away from wells. So now you can start creating volumes of expected rock physics properties and AVO signatures away from wells in a 3D volume. We have a lot of publications on this over the last few years, both in geophysical prospecting and first break. So it's a technology that is out there and available for anyone to create. So yeah. And let me show you an example from the Glitne field first in the North Sea. To the left here is a seismic amplitude map on the top surface of a submarine fan. You see the feeder channel, so of a turbidite system. Yellow is pretty much where the sands are located, and you have some well locations, well 1, 2, and 3. And here are some AVO signatures recorded from the data. So these are real observations from outside the map, but we have data here as well. So you see that it is penetrating the feeder channel. And it has what we call a AVO class 1, a hard response, hard reflectivity with a negative AVO gradient. It's changing completely to well 2. It's a soft negative intercept, a negative gradient. You call that a class 3 AVO response. And then it's back to a class 1, more similar to well 1. So something is happening here. Turns out this is an old discovery. But it also turns out that big changes in seismic signatures here are not only related to the what's inside the container, the pore fluid, it's also affected by the container. Remember what I talked about, the Coke bottle and the balloon here. Because what we're seeing here is that we're going from a feeder channel where you have more cement, and then you have unconsolidated soft sediments on the lobe top, and then back to a more consolidated rock. So what you see here is not only a fluid response, it's also the effect of phases and diagenesis. And here's just a cartoon of the geology of this field and some thin sections in well 2. So we have quite clean sands, well sorted, but with some variability in the grain sizes. And the grain sizes also plays a role here. The 3 wells, if you look at the data and highlight the sandy interval that is a key target, this upper Heimdall fan here in light blue. And here is the sandstone depth trend that I modeled with a Valderhag model into the rock physics model, entering the frying pan, the cementation. So you see that we are just into the cementation domain, and you can actually see that in the data. Okay, but the very top of this well too is actually still have some unconsolidated rocks at the very top here, which are actually important to honor at the very top, which we'll get back to in a little bit details. But overall, the pattern is that we are entering this, just entering the chemical compaction domain, and the rocks are getting cemented. If you look at the crossplot from that well too, we see that there's some variability in the velocities. And we actually have rock physics models and tools to quantify the cement volume from rock physics models. So you see here that it vary from almost 0 in the upper part, unit 1, to more cemented in unit 2. And here is actually, we do this combined modeling of rock physics, impedance and VPVS ratio for the top and further down deeply into the reservoir. And you actually here explain the properties quite well at the top surface. And we see that just entered the reservoir here. And we expect an ABO class 3 soft negative. And that's what we saw at that well. Remember, that was actually the real observation, this one. So it fits with what we modeled. The band here is just a Monte Carlo simulation with some variability. Good separation between water response in blue and oil. So we predict this. If we bury deeper and went deeper here, you actually switch. Your ABO signature will be different. See, it's positive. Just because you're entering more deeply. So you get also more overlap and less separation between brine and oil. Remember the Coke bottle. You're getting more into the Coke bottle domain, huh? More difficult to say what's inside the container, but still you have some separation. Yeah, and the key parameters here, of course, the temperature and the depth, the grain size, and also there's some clay coating at the top here. So now I'm going to play with some what I call multi-scenarios modeling. So I can test, because I have these rock physics models constrained by geology, I can vary some of this temperature. Let's say there is some uncertainty away from wells with temperature gradient or grain size. These are 2 key parameters. So I can play with these. Let's now start, and here you see the data from the well 2, and the ellipses are including some variability. So I'm doing Monte Carlo simulation based on the models around this ellipsis that create this ABO. I'm going to change these parameters a little bit. I just changed the grain size from 0.2 to 0.4. You see how actually my ABO response is changing. So based on that. But this is softer than what I see in the data, so it's probably not a realistic one. Also, the temperature gradient changed to 30. Let's see, 0.2. Yeah, so here I changed the temperature gradient here and the grain size. Now I get a very soft response, but it's you see I'm undershooting. I'm not fitting really the data. But the 40 degrees, much higher temperature. You see that I put my frying pan start earlier. But now you see I'm over predicting. It's probably on the other side, so it's getting too high. So that's probably not the correct model either. So you see here that this is the correct one, but you see that by changing these parameters, I can see how things change away from wells if some of these parameters change. I can do this in 2D. So here I'm just picking the one that is more reasonable. Scenario 1, weakly cemented due to partial coating of quartz grain size 0.3, temperature gradient is 35. and I'm doing it at around well 2 here. And here you see the AVO class and the cement volume that is predicted from Valderhaug, which is now almost 0. And here you have the porosity around 29–30%. And then I'm gonna change the scenario to moderately well cemented. Actually, what I changed is only the grain size. And the clay volume is a little bit less. So I'll go from this to this one. And you see that the cement volume is starting to pick up. It turns out that the grain size is affecting the surface area of the grain, which again affects the cement volume. The more surface area available, which will be for more smaller grains, the more easily it gets cemented for the same temperature history. This is a little bit complex into the geochemistry and diagenesis, but it's how it works. So the smaller grain size sandstones tend to be more easily cemented than the more coarse grained for the same temperature history. And that's what we see here. And that will affect your reservoir properties. And if I combine these two scenarios into a hybrid modeling with a transition from unit 1 to unit 2, remember I had 2 different units with 2 different grain sizes, I can predict more what I expect to see in the AVO classes to the left here. And if I look at the fluid factor, which is an attribute, AVO attribute created from intercept and gradient, I have the model one here, and I have actually the observed data. So you see, it actually predicts quite nicely where I expect to see the fluid factor here. And remember, this well is a dry well just at the fluid contact. So there are some differences in the data. I see something here that I don't see here. Could be noise, or it could be something that my model didn't include. So, yeah. And this presentation is actually included in a chapter just published in a book recently. It came out in last year, Deepwater Sedimentary Systems, chapter 16. We also have a chapter on rock physics and machine learning, where we go more into the QI in chapter 17, if you want to look into that. Okay, the second case example is from the Barents Sea. So now with an area where you have big uplifts. So here I live in Oslo here, but Norway is quite extensive long. So it's about 1,500, 2,000 kilometers up here to the Barents Sea. And this is an area where we are exploring for gas and oil as well. But this is an area where it's actually part of the shield or the continent of Norway. So it has been uplifted quite significantly. So around 2,000 meter uplift. And that needs to be taken into account. And we see that, for example, if we have a well, and this is exactly the same exercise, it looks quite busy, but it's exactly what I showed you in the beginning, this 4-step modeling from the burial history, the dynamic modeling of the cement volume and the porosity, including that, inputting that into the rock physics model to predict the velocities. So you see here, I'm modeling the burial history here is actually, I'm testing 2 different scenarios. I'm doing one that I'm just barely touching the 70 degrees, but I'm not entering the frying pan, and the other one where I'm just barely dipping into it. And you see the effect on the velocities is very different. In the first scenario, where I didn't enter into the frying pan, I get an unconsolidated sediment, but my measurements are here. If I zoom in, you see that I need to dip into the frying pan to explain this one. So there has been some cementation starting, and we see that in the thin section, that the coarse cement has started gluing the grains together. And this will affect your rock physics properties. So, and this is also a way to quantify the uplift. And even though it's just 1 or 2% cement, it's enough to explain this jump here. So we have the modeling explaining these data. And if you looked at the expected AVO signatures, gradient versus intercept, they will be very different for the unconsolidated case and the slightly cemented case for water, oil, and gas in red, green, and blue. Okay, and we actually see that this is we can compare this modeling also with synthetic seismogram modeling at the well location. And here is a case with the brine and oil, and you see here that in this is a nifty exercise to do also to test if you have some tuning effects of the signal and phase distortions and stuff. So this is a synthetic gather at the well location, where you see that you go from a red hard to a blue soft. at the brine to a blue to strong blue or yellow at the far. So this is a class, what we call 2P to 2. And this is pretty much what you see here, going from this scenario to this one. So it's a negative, slightly negative, becoming more negative because of the gradient. I know some of you probably didn't have AVO in your courses, but and that's something I can also go through more in detail later. So just take this for granted. But it's a very useful tool to discriminate fluid and lithology effect from seismic, which is it showing. But again, remember the container. You have another well where you have been burying things deeper into the subsurface. And now the rocks are becoming more hard and stiffer. And you plug in, you do the same exercise, you got more cement. It's about 9%, 10% cement. Porosity is much lower and velocity is much higher. And you see here, you plot at higher velocities and lower porosities. And your AVO signatures have moved into this area where you see that there is much more overlap and more difficult to discriminate water and oil. So, and this we can do in a big area, and here I show some maps. So you see a present day, this is BCU, base of Cretaceous unit. So my reservoir is actually just beneath the BCU. So here you see the present day, and we have created an uplift map from the seismic velocities over a huge area. So the wells I just showed you were this one and another one just outside this one, but anyway. You see here the maximum burial, which is the present day, adding the uplift, you get back to the maximum burial. And then we can also look at the temperature at the maximum burial. And this tells you something about how much it has been cementing. So we actually use this information for our combined burial and rock physics modeling. Now, not only at the well location, but between the wells. We can do exactly the same 4-step exercise that I just showed you. I can show at any location between the maps. Okay, so let's do that. I'm going to show you next slide. Yeah, so here now I do the modeling for any location in this map. So this is a forward modeling of the exactly this 4-step modeling, the burial history, the Walderhaag dynamic modeling of the cement volume and the porosity, plugging it into the rock physics model to predict the velocity evolution. I do this for p-web velocity, but also, not shown here, shear-web velocities, and of course I have the densities since I have the porosities. Let me just explain. The orange points here are the present day depths, okay, these endpoints. The other orange points at the other side here is the maximum burial, and then it's just connecting between those. The horizontal dark gray models or lines are the transition between mechanical to chemical compaction, which will vary because the temperature gradients are varying in space. So these are just simulations at different locations in these maps, okay? So now I've done this modeling not only at the well locations, but in the map view. I also need to create AVO plots. I need to have an understanding about the caprock shale trends, not about only the sands. Shales are more difficult to model from physical models like the Walderhaag combined with rock physics contact theory. So we create these empirical depth trends for shales, because shales are located present in most of the wells. So these green dots or circles are average values for 10 different wells. So we can actually create quite robust depth trends for different shale intervals. The one I'm going to look at is actually this Fuln, which is a caprock of the reservoir I'm going to look at. And here I'm just showing that you could use power law or linear laws, and there are different laws, but I prefer the linear ones here, and the linear one and green one fitting this one. Anyways, if you have these shale and sand, so now I have a shale trends and I have the sandstone models. This is as a function of maximum burial, by the way, for the shales. So then I can plot the elastic properties in the map view of the acoustic impedance and the VPVS, both for the caprock and for the reservoir sands here. So you see how they're changing from high values in areas where you have large maximum burial. So that's where you get the Coke bottle, and blue is where you get kind of the balloon, nice softer settings. And here is for a given scenario where the grain size is 0.3, you have no clay coating, temperature gradient is 38, clay volume is 0.1, and I assume it's oil inside the reservoir. Okay. Then I expect to see these different AVO classes. So the AVO classes is about the location in that cross plot of the intercept and gradient. So you see now that I have different AVO class 1 in this western region, and class 3 to 4 in this eastern region, and maybe class 2 here. These are usually more softer AVO responses for representing where you expect more fluid sensitivity. Meaning that in this western area, we would not be able to see very much difference between oil and water, and that's what you see here. You see it's blue here and blue here. But in this eastern region, you see more changes going from water to oil. So and that's why we call it visibility maps. It tells us where would you expect to see changes in your AVO signatures when you go from brine or water to oil or even gas, okay? And then we can test with different parameters, of course. And I'm just comparing this with, of course, it's constrained by the uplift or net erosion map that we estimate from the seismic velocities. So we're bringing in geological information from the seismic velocities to say something about the expected reflectivities that we can get from the amplitudes in your seismic. And then we can go in detail and assess, let's say, a given prospect. And this is just showing that with a constant temperature gradient, for example, here, we would not see changes between the different fluid scenarios, but for the case where we actually see varying temperature gradient, we actually see changes from the water to oil to gas. So it also shows the importance of better modeling the temperature variations. And that's something we can actually do by kind of a 1D. What we've done here is a simple basin modeling of the temperatures. And that could also be done more complex with a heat flow modeling where you actually honor the change in temperature, not only spatially, but also through geological time. And that's something we are actually also doing research on. Okay, so then if you make a cross plot, we can actually create pseudologs at any locations here. But remember, we not only have the map view, we actually have a volume, but we can create this for the top reservoir, or for the, in this case, it's called the stir formation of Jurassic age. And the small circles here are from the wells in the west, are the blue, and the wells in the east, where you see you have softer sandstones in yellow, and in the prospective area where we haven't drilled between, we expect to be here, okay? So this already tells us something about the expected velocities and expected porosities. Yeah. Okay, so yeah, another thing, I'm going to zoom into this eastern area because I worked in this area quite a lot, and we're going to show some results during EAG at Vienna on this one. So I'm just giving a little bit teaser on that because I think it's quite interesting. And here we see that we have some through the caprock time to the reservoir time. You see some interesting changes in the stratigraphy that we need to honor. And this is zooming into this eastern part, and we have more wells here. But there is also a local trend here going from south to north here, where you go from more soft shales to slightly more silty shales. These are pie charts of distribution of these actually classified from the rock physics models. We also see the same for the sandstone interval right below that. You go from more clean sands to slightly more heterogeneous sands in the northern part, and it's related to going more from beach to more offshore sediments. And this will affect your rock physics properties. And what we see is actually, without going into the details here, we tend to see this dispersive play trend going from the reservoir, where you see a deteriorated sorting trend from high porosity to lower porosity. And then the caprock is more on this side, where you have the silty shale lag. But we actually have models that can capture this transition. And you probably have transition in your stratigraphy going from a clean beach sand to more offshore marine and a draping caprock shale. So here is even the question, when is it a caprock and when it is a reservoir? Because you have this transition. And this is also important for your AVO signatures because we're actually looking at the transition between the caprock and the reservoir. So there is depositional properties here that we need to honor. But more importantly, it's probably the compaction variation. Going from that more southern to the more northern part, we also see a tilt. And then we have estimated uplifts using the seismic velocities, and we see that the maximum burial has been larger in the northern part here. So the reservoir rock is actually stiffer today in the northern part of this region. We created this 3D volume. So these are the 3D AVO feasibilities. We have uplift maps that we have quantified using background shale trends. I'm not going into the details here, but it's just comparing a relatively normal compaction trend with your observed seismic velocities. You can estimate your uplift, and you do that at any location. So you create this uplift volume, and then you plug that into the diagenetic modeling, Walderag, and you create the cement volume, and then you predict your expected AVO signatures. I can show it in the map view. It's a little bit easier to see. So here you see the uplift map in the lower left. You see the cement volume, and here you see that it's unconsolidated in the southern part here, but getting more and more cemented, increasing cement northwards here. And that you'll see is affecting your AVO classes, going from class 2 to a class 1 northwards here. And also remember here we're honoring both the compaction and the depositional trends together. So it's quite complex. So we're integrating a lot of geological information to constrain this. But of course, the cement volume is a key driver. So you see the AVO classes are also affected by the uplift. So it's a combination of the depositional trend and the compaction and cementation is affecting this plot. So this is a top reservoir horizon. So now I can compare with some wells. I have some wells where I can compare with and these rock physics models that I have actually honor the cement volume. Remember these wide bounds I showed in the very beginning of the talk, but then we have more details, contact models that actually honor the cement volume. And if you're on the gray line here, I have a loose sand model, but with some pressure. So this is only mechanical compaction. And then as I add more and more cement, I will climb upwards through here. But in the southern part here, this is actually outside, it's unconsolidated. And I see my sandstone data are plotting here. And this is actually where I expect to be. I go northwards, and now I'm inside the map. You see it's just above the gray line. So it's pretty much unconsolidated as I see in the map. And here I see a cartoon with the burial history. So I'm going to go deeper and deeper as I go northwards. Let's see how the data. So these are well-log data to the left. This is the expected cement volume from the volume modeling in the 3D to the right, constrained by the uplift map. Okay. And then I go actually outside and then inside again. And she is starting to pick up more cement and climbing here, higher velocities. I'm diving more into the frying pan. And here's this one. And now I go to this area. It's actually more poorly sorted. You also see a sorting trend here along this one. And here you have more cement. You're climbing up and more cement. So you see, and now you see I've been in this one. So you see I've gone from unconsolidated to more cemented, harder rocks. You also see how the caprock in green has evolved. So there is also cementation happening in the shales. That cementation is also related to smectite to illite transition. But probably also what you see here is these connected tails here. And that's what I told you about these dispersive changes. You have these transitions. So you not only have, in the south, you tend to have more pure shales and sands, but in the north, you tend to have more mixed between the shales and the sands. So you're kind of connecting the poorly sorted sands and silty shales. So there's a combination of diagenesis and the depositional sorting of both sands and shales here, getting a complex pattern. But by doing this exercise, we can actually model it, and it shows that we have a power to say something about how it is in between the wells. And here I'm just showing the predicted porosities, and then I see the well locations here, and it's yeah. So So yeah, and then just at the end, I can show you here that we can then play with scenarios and test, for example, different grain sizes to see what are the expected properties at any given depth. And this we could do at south-of-well locations if we have prospects, for example, away from wells, and actually see how so you go from this to this, you see how, and then again, this is the fluid factor is kind of this Coke bottle syndrome. The deeper you get, the less able you are to separate hydrocarbons, whereas if you have soft rocks, you're more easily separated. And the AVO classes will also change as a function of the grain size and the temperature, of course. So I think this is just a demonstration of how we can use this tool at any given locations and display how we expect to see changes. Okay, I'm not good. I think I've got to get to the end. Just to summarize, we've shown a novel interdisciplinary methodology for generation of rock property and AVO visibility maps or cubes to be used in subsurface characterization and prospect de-risking. And this methodology enables rapid extrapolation of expected rock physical properties away from well control. We can do this in a multi-scenario way and test different scenarios. And in that sense, we're capturing or assessing uncertainties. And we can assess also alternative models away from well controls. Of course, there are uncertainties related to temperature history, grain size, and sorting, and clay volume, and so on. So finally, I would like to thank my colleague Ivan Leowski at DigScience and Nils Bakke at Aker BP for valuable discussions. And Aker BP and Spirit Energy has been supporting financially the development of this technology. And here's just an example that we can also do this. Is some current work we're doing on using exactly the same workflow for pore pressure prediction and expected effect changes on your velocities. Yeah, and also here is kind of we published in the first break paper, a collaboration with PGS, where we integrated this with QI work. We actually used feasibility modeling to help us classify AVO data. So if you have the acoustic impedance and VPVS inverted from data, you could use the scenario modeling and test with different scenarios. So you have the base scenario, and then you change some parameter, let's say the grain size or the uplift uncertainty, and you see how that affects your classification of, let's say, the oil in green here. And that will, of course, be a function of your input parameters. So you can do a live classification and QI study constrained by these feasibility modeling. And this is kind of the current research and work we are doing as well. So with that, I think I stop at the summary here, and I'll be happy to answer any questions from the audience. Thank you very much.
Okay. Thank you, Avseth, for the very interesting topic about rock physics and AVO analysis for the reservoir characterization. Now we have a couple of questions from the audience. First is, it's direct question from, yes, Miss Denia Angeline. Please introduce yourself, and yes, direct question to Mr. Avseth. Go ahead.
Thank you so much for Mr. Pahandoyo for the experience you gave me. It's so vulnerable for me to talking with Dr. Avseth. Of course, thank you so much, Dr. Avseth, for the insightful materials today. So I have maybe two things to ask you. For the first one is how to create 1D to 2D and 3D models in rock physics. Are there any specific or maybe a lot of wells and or other combined geophysical data it's need from there? And the second questions. So in Indonesia today, we're right now planning about net zero emission carbon, and we're gonna drive that net zero emission carbon to carbon capture and storage. From there, I would like to ask, are there any possibilities for AVO methods to maximize the injection or characterization to CO2 in CCS process. Thank you so much, Mr. Avseth.
Yeah, thank you very much. Very good questions, both of them. I'll start with the first one. So how do you kind of extend this approach from 1D to 3D? So what I showed in the beginning comparing with the well location was to do this in 1D. Okay, so I did compaction modeling with depth and then uplift, and I did that in a 1D. So when I showed it in the map view, I need to bring some information about this burial history away from wells, and that is brought in by the seismic velocities. So I actually bring in information from the seismic velocities, which I convert to interval velocities. Sometimes I can use FWI velocities, which is already a very high resolution interval velocity sometimes. So that's sometimes even better. So then if I have that, I briefly touched on how we can create these uplift volumes. So then I go into a key interval, let's say a shale interval, where I know I have a thick, massive shale. And I then map close to my target reservoir. And then I compare a normal compaction trend, which I can get from the literature or from some well or area where I know I have normal compaction. And then I just compare my observed velocity trends along that, within that volume. So I can create the volume of uplift for that target interval. Now I have a tool to change my 1D. So I'm actually just updating that 1D model at each location in the grid or the volume. So I'm actually just repeating the 1D modeling in the 3D sense. So in that sense, I'm still doing a 1D rock physics modeling, but I'm doing it at any location. So that's why I can call it pseudo well locations. So I'm doing just very densely pseudo well location 1D, and I group it together into a 3D volume. But the information to constrain the modeling at the pseudo well location is coming from the seismic velocities. So it's kind of course, we could extend it a bit to for example, knowing that the tectonic movements, of course, are not only happening vertically, they're happening in 3D. So we could, of course, do this even more advanced by linking plate movements horizontally or not only vertically, and do that in a 3D sense, and then have an even closer link to that. But so we're kind of cheating a little bit on the tectonic, just looking at the vertical movements, even though it could be a movement that is both vertically and horizontally. So that's, of course, some uncertainty there. When it comes to temperature gradients, we know that those can change in 3D. So heat flow modeling can be done in 3D, and basin modelers actually do 3D heat flow modeling. But that has a lot of uncertainties also when it comes to the input parameters. So we find it more useful to do also the heat flow modeling in 1D, or just assume some temperature gradient in space. So constrained by well log observations. Usually we have the temperature history at well locations. So there are a lot of assumptions, and so we actually just, you can say the modeling is not really a 3D wave propagation modeling. We're just looking at 1D rock property modeling, but repeating the exercise in a 3D volume, you can say. Of course, if you wanted to include honor stress anisotropy, and then you get your elasticity tensor is actually have several dimensions. You could also, in some cases, need to link that and actually do the rock physics modeling, honoring the fact that properties can change in different directions. We haven't done that here. We assume anisotropy. We have also implemented our tools, but I didn't show it. VTI anisotropy in the Caprock shales is important, but you could also have stress anisotropy in your sands. Cracks, you can honor that. So there are a lot of things you can add and add and add. So yeah. So I think that answered the first question. The second question is on CCS, and of course that has great focus also in Norway. We have been slightly involved a little bit in it, and it's probably going to be increasingly important here in Norway. We see that, and the tool or the methodology that I showed you today, I think can be very useful to say something about, do a feasibility study on the expected rock physics and seismic signatures of a CCS aquifer, because it's very important to monitor how the CCS sequestration is looking in your seismic through sequestration to avoid leakage, for example. And then we're into the 40 problem, and we're also looking into that, looking at rock physics and AVO feasibilities in 40. So I think to extend this not only from 3D but to 40 and to apply it to CCS or sequestration, that will be one of the key paths that we're going to follow, of course. So, and if someone of you are looking into these problems and issues, that will be also very interesting, I think. It's and also for geothermal, to do feasibility for geothermal aquifers. So to do exactly the same exercise for that. So yeah, maybe at this occasion, I should also answer the question that is written in the chat by Andika. My question is, what things need to be considered in choosing a rock physics model? And that's a good question as well, because I selected some of my call it favorite models that are very useful for high porosity sands and sandstones. You could be in carbonate environment, or you could be very deeply buried with very tight sands with cracks. Then my high porosity contact models are not as good. I think I showed it in briefly in, if I go back to the table. Here was on in the beginning. Yeah, here, rock physics modeling. So you see how different actually strategies. If you're very deeply buried and then uplifted, you see there are some inclusion-based models. I didn't mention that here, but these are actually, and we even have some hybrid models, and we have tested that in the Barents Sea actually, where we honor cracks and not only what is happening at the grain contacts. I could later at some point also give a lecture more on the rock physics theory and different models and actually talk more about that for you. But there are different models for different rock types. When you are in a very tight rocks with cracks, for example, it's important to honor the effect of pore shapes. Carbonates as well, pore shapes are important to control the elasticity. Whereas in these high porosity sands, it's actually what's happening at the grain contacts. And then we have these granular models, contact theory, and friable sand models, and contact cement models that are very useful that I used. But if you, so yeah, so the different models could be chosen based on the scenario. For example, here, we're actually switching between the Hertz-Mindlin model when we're in the mechanical compaction domain to the contact cement models when we're in the chemical compaction domain. So there are different models for different burial regimes, but there could also be different models for different geological settings. And in fact, for carbonates, this burial, linking it to burial is much more difficult because carbonates tend to have chemical compaction even happening very shallow, and it's not easy to predict depth trends in carbonates. So we would probably have to use a different strategy to do the same exercise for carbonates. And I haven't, strictly speaking, I haven't worked that much with carbonates. Okay, any other questions?
Yeah, we have one more question. Yes. From Muhammad Excel, please.
Okay, sure. Thank you for the opportunities. I'm Muhammad Excel Putra, second year student geophysical engineering from Sumatra Institute of Technology. Thank you for your insightful presentation on this topic. I have a question that I would like to ask for you, sir. How can change? The first question is, how can changes in the fluid content within rock affect the physical properties of the rock, and how can this be considered in rock physics models? And the second question is, how does deep and fluid sensitivity affect the AVO detection capabilities? Thank you in advance for taking the time to address my question. I look forward to hear your question, sir. Thank you.
Okay, yeah, so I briefly touched on those things, but of course I didn't have time to go into the details in this kind of overview talk. So if I understood you correctly, the first question was how the changing fluid content will affect your rock physics properties. So I think if I go back to this one here, so I'm gonna just move this one again. Okay, here. So we have this what we call the Gassman theory. So that's a fundamental theory that's based on first principle, actually. So it's but it has some limitations. It assumes connected porosity. It assumes one type of mineral, among others, isotropic rock. And this is a simple version of that one. So what we measure of the whole rock is on the left-hand side here, okay? And that's the ability for you to compress the whole, let's say, container with the fluid inside it. So you feel both of it, okay? Which will be a function of the glass itself, that's a mineral part, and what's inside the container. That's a pore, you can call it the void space, okay? Which includes both the void itself, but also what's inside the fluid. And you see here that if this is what we call a stiff fluid, meaning that this K fluid is increasing. For example, a heavy oil. Okay, you're putting a heavy oil or into this one. This parameter goes up. Okay, if it's if it's a very soft fluid like gas, this one is very low, small. Okay, if this number is small, it means that you're dividing on a smaller number here. If this one is small, you have a more dramatic effect on your overall saturation. So if I can draw it, I think I'm gonna change to a pen here. So I'm gonna draw here. I'm gonna draw. Try to sketch it. So I'm gonna do like this. So if I call this saturation of water. So let's say I have 0 here, and that's 100% gas, and then 1 here. So this on vertical here, it could be the your incompressibility here, or your velocity. It could be your velocity, for example, VP. Okay, which has this one as an important parameter. Okay, so when I put a soft gas here, just a little bit of it will actually cause this one to drop quite a lot, very easily. And then what we see is actually that it goes a little bit up here. So you have this compressibility effect coming in very, very quickly, especially if you have a soft rock. If you have a stiffer fluid, this one will be more gentle, okay, like this. And then it's something like this, okay? So this one can be estimated for any saturation, and you see that the effect is more dramatic on for a softer fluid than a stiffer fluid. But also we see that this one is important. If you have a softer rock, means that this sensitivity is larger, is smaller. If I now put a stiffer rock, I usually see for the time. So this could be. Let's say this is a gas and this is the oil for a soft rock. For a stiffer rock, I see the gas effect is maybe like this. Oh, I know this should be going like this, and the oil is maybe like this. Okay, so the higher velocities and the sensitivity is much smaller. So this is just estimated from this equation, and this goes into, you know, that the VP equals to the square roots of K plus 4/3 shear modulus over the density. And this K, this is for the rock. This is the one here. So when you do this exercise here, we know this one for the mineral, we know it's kind of looked up in the rock physics handbook. And then this one, also the fluid properties we usually know, the porosity we can constrain or know from depth and modeling. And this one also is with a rock coming from a rock physics model away from wells and can be calibrated with wells. And then you can do this exercise here. And that's pretty much what I did in the study. I didn't show it, but I did this exercise for different fluid scenarios and testing it. Okay, so and the shear model is insensitive to fluid. It doesn't, because the K is trying to change the volume of something. It's compressing. So it's called the incompressibility. The shear is just trying to change the shape of it, but it's unaffected of what's inside. And the density, of course, will be affecting a little bit. There is an effect of the fluid, and that's why you see actually the very beginning here is the compressibility effect of the K that is most important, but it's turning a little bit here. It's actually dividing on density, so a lower number here for a lighter fluid is actually causing a slight increase. That's why it's actually a nonlinear effect. So you see it increase a bit. That's a density effect coming in. But this is the bulk effect from the K dropping. So, and that's overall, it's a drop. So the K effect is more important than the density effect on the velocities for the change of fluid. So exactly this kind of related to your question, I think, in details. I think we could later go through more details on this, but this is really what's behind this calculation when you see, for example, here. You see here, going from brine to oil, I did this exercise, but I go from 100% brine to, let's say, 100% oil. So I just did the end members. So I did exactly this exercise I just showed you. And I did this also here. I did this exercise. This is coming from the Gassman theory. So estimated. So I have a very good, and the Gassman theory is quite robust and it works and it's quite nice. So yeah.
Yeah. Okay, thank you, Avseth. I think the time is over. We have 10 minutes more.
Yeah, very good.
Schedule.
Good question.
Yeah, before we close the webinar, I think we need your closing statement to motivate our student in Teknik Sumatera to maybe learn more about rock physics and quantitative seismic interpretation. Please.
Absolutely. Yeah. Sounds good. Yeah, I'm looking forward to continue collaboration and hopefully also soon drop by live.
Yeah. Okay. Yes, Pak Rector still here. Yeah, Pak Rector, thank you again for coming the webinar, and once again thank you for Avseth, Dr. Avseth, to give the lecture to our student and also to be our honorary professor in ITERA. Yes, see you soon in Sumatra, in Lampung province. Yeah. Okay, thank you.
Thank you very much. Have a nice day.
Avseth.
Thank you. Bye-bye. Have a nice day.
Bye.
Bye.
God bless you.
Thank you, and likewise.
Thank you.
Bye.